Hello everyone, in today's video we'll be discussing on Thevenin's theorem. Here is the content for today's video. Firstly, we'll discuss about the introduction to Thevenin's theorem, followed by Thevenin's theorem basics, Thevenin's theorem, numerical, applications, limitations, comparison with Norton's theorem, Thevenin's theorem in circuit design, and finally the conclusion. Introduction. Thevenin's theorem serves as a powerful technique in electrical engineering, enabling the simplification of intricate electrical networks. By replacing a complex network with an equivalent Thevenin circuit, engineers and technicians can streamline circuit analysis, significantly reducing its complexity. The application of Thevenin's theorem proves invaluable in the practical analysis of circuits, offering a method to efficiently model complex networks for easier understanding and calculations. Thevenin's theorem basics. The Thevenin equivalent circuit is composed of a voltage source and a resistor, providing a simplified representation of a complex electrical network. In this model, the voltage source corresponds to the open circuit voltage at the terminals of the original network, and the resistor is termed as the Thevenin resistance. The use of the Thevenin equivalent circuit simplifies the analysis of the original network by distilling its essential characteristics into a more manageable and comprehensible form. Thevenin's theorem. Here is a statement for Thevenin's theorem. In a linear bilateral network with open terminals A and B, Thevenin's equivalent circuit can be represented by a voltage source VTH in series with an impedance ZTH. The Thevenin's equivalent voltage source VTH is determined as the open circuit voltage measured across the load terminals A and B. The Thevenin's impedance ZTH is calculated by measuring the total impedance of the network from the load terminals, making all sources in the network as zero. Here is the proof for Thevenin's theorem. We are considering the network as shown below. Further, applying the current division rule or branch current formula to the branch of the network consisting of the load resistor, we can further obtain the load current equation as R2 by R2 plus R3 plus R1 into I. This load current equation is considered as equation number 1. Further, in order to obtain the equation for the current, we rewrite the circuit into a much simpler network. And the resistor R2 parallel R3 plus RL is further simplified. From the above network, we obtain the equation of current as shown in equation number 2. Hence, substituting equation number 2 in equation number 1, we obtain the load current equation as R2V by R1R2 plus R1R3 plus R1RL plus R2R3 plus R2RL. And this load current equation is considered as equation number 3. Further, the verification of equation 3 is done by applying Thevenin's theorem. The step 1 is to find VTH. In order to find the Thevenin's voltage, it involves opening the circuit at the designated terminals and determining the voltage across the resulting open circuit. The voltage obtained through this process is termed as the Thevenin's voltage, representing the potential supplied by the network when connected to a load. Here is the simplified network in order to calculate the Thevenin's voltage. VTH is equal to R2. Further, the equation of the current I can be written as V by R1 plus R2 from the above network. Substituting this equation of current in VTH, we obtain the equation of VTH as V by R1 plus R2 into R2. Step 2 is to find the Thevenin's resistance RTH. In order to determine the Thevenin's resistance, the process involves deactivating all the independent sources within the original network. The equivalent resistance is then calculated at the terminals of interest, providing a measure of the internal impedance of the network. This step is crucial in establishing the Thevenin equivalent circuit as it captures the inherent resistance characteristics of the original network when independent sources are temporarily removed. Here is a simplified network in order to calculate Thevenin's resistance RTH, and RTH is equal to R3 plus R1 parallel R2. Further simplifying this equation, we obtain the equation for Thevenin's resistance as R1 R3 plus R2 R3 plus R1 R2 by R1 plus R2. The third step is to write the equivalent circuit connecting a load resistor across the terminals A and B. From the above network, we can obtain the equation of load current as IL is equal to VTH by RTH plus RL, where VTH is the Thevenin's voltage, RTH is the Thevenin's resistance, and RL is the load resistor. Further, the load current IL is simplified by applying the obtained equations of VTH and RTH. After simplification, we obtain the load current equation as VR2 by R1R3 plus R2R3 plus R1R2 plus R1RL plus R2RL. And this equation of the load current is considered as equation number 4. Hence, comparing equation 3 and 4, both are equal, hence the Thevenin's theorem is proved. Numerical based on Thevenin's theorem. The numerical states that by using Thevenin's theorem, find the current flowing through 6 ohm resistor for the network shown below. So the step 1 is to find the Thevenin's voltage VTH by removing the load resistor of 6 ohm and finding the open circuit voltage across the terminals A and B. In the network shown, the 5 ampere current source is connected parallelly to a resistor of 4 ohm, which can be converted into a voltage source in series with the resistor of 4 ohm by applying the equation of V is equal to IR. So further, the simplified circuit will consist of a 20 volt voltage source in series with a 4 ohm resistor. Applying KVL rule to the loop 1, we obtain the value of I1 as minus 2 ampere. Further, in order to calculate VTH, we have the equation VTH is equal to VA minus VB, where VB in this network is 0. VA is equal to VTH, and the value of VA is obtained as 7 volt, which implies that VTH is also 7 volts. The second step is to find the Thevenin's resistance by making all the sources in the network as 0. So further, RTH is calculated as shown. That is, RTH is equal to 4 into 4 by 4 plus 4 plus 2, which is equal to 4 ohm. Further, we write the Thevenin's equivalent circuit, where RTH is of 4 ohm and the load resistor RL is of 6 ohm. Therefore, the current I is equal to VTH by RTH plus RL. By substituting the given values, we obtain the value of current as 0.7 ampere. Applications. Thevenin's theorem is widely applied in electrical engineering, serving as a valuable method to simplify complex circuits across a range of applications including power systems, electronic circuits, and telecommunication networks. In the realm of AC circuits, Thevenin's theorem remains applicable, offering an equivalent circuit comprising an AC voltage source and a Thevenin's impedance. The extension of Thevenin's theorem to AC circuits enables engineers to conduct simplified analysis, providing insights crucial for circuit design and efficient analysis in AC network scenarios. Limitations. Well, despite its power, Thevenin's theorem has limitations, being excessively applicable to linear networks and unsuitable for circuits containing nonlinear elements like diodes or transistors. The theorem's accuracy is contingent on steady-state conditions, posing a limitation as it may not provide reliable results for circuits undergoing time-varying dynamics. Engineers should be cautious when applying Thevenin's theorem, recognizing its constraints and opting for alternative methods when dealing with nonlinear components or time-varying circuits. Comparison with Norton's theorem. Contrasting with Norton's theorem, which employs a current source and a parallel resistor, Thevenin's theorem presents an alternative technique for simplifying circuits. Both theorems yield equivalent circuits, yet the decision between Thevenin's and Norton's depends on the unique analysis, demands, and characteristics of the original network. Engineers choose between Thevenin's and Norton's theorems based on the specific requirements of their analysis, considering factors such as ease of application and relevance to the nature of the original circuit. Thevenin's theorem in circuit design. In circuit design, a profound understanding of Thevenin's theorem is imperative for the development of efficient and reliable systems. Through the simplification of complex networks, designers can optimize circuit performance, streamline component count, and mitigate overall design complexity. The application of Thevenin's theorem offers a systematic approach in circuit design, empowering engineers to create well-organized and optimized systems for various applications. Conclusion. In conclusion, Thevenin's theorem stands as a potent and adaptable tool for network analysis within the realm of electrical engineering. The theorem's capability to streamline intricate circuits, along with its broad range of applications, establishes it as an essential concept for both engineers and technicians. Proficient comprehension and application of Thevenin's theorem empower professionals to conduct efficient circuit analysis and design, contributing to the creation of innovative and reliable systems. Thank you.